Now let's take a look at the equation to calculate the change in only enthalpy for a single phase region. Here's the equation. We'll derive it in a second, but let's take a look at this equation. It says if I want to calculate the change in enthalpy from a state 1 to state 2, it's the integral of c sub p dt plus the integral of 1 to 2 of something dp. So something integrated with respect to temperature, something with respect to pressure. How did this equation come about? Well, we can derive it. Here's the derivation. It's in the textbook, so I give you kind of a Cliff Notes overview of it. But it gives you a sense of how this whole chapter is put together. We start with S is equal to assumed to be a function of temperature and pressure. Then you can get through chain rule. ds excuse me, ds is equal to the partial of S with respect to T, holding pressure constant dt plus blah, blah, blah. You use Maxwell's equation to go and change out this part right here, one of Maxwell's relationships. So there you go. Now we have ds is equal to a function. Stop. Do that for h. H is assumed to be a function of temperature and pressure. Chain rule, dH is equal to law of that. And then by definition, what is specific heat, constant pressure, C sub P? Is that by definition the partial of H with respect to temperature holding pressure constant? It is. Where did we see that before? All the way back at chapter 3. Go back and take a look at specific heats in chapter 3 of this textbook. So we substitute there. We also can recall that dH is equal to TdS plus VdP. Where did that come from? When we were introduced to entropy in chapter 6 of the textbook. So you take and replace dH. So you use this equation for dH and substitute into the left-hand side. And then on the right-hand side of the equation, substitute for ds in the TdS right here. And then boom, you get this long. So this was all brought in from dH. You have T times ds plus VdP. Doesn't look like we're getting anywhere, but you regroup the terms. So everything times dP is equal to everything times dt. So you group your terms, and then you say to yourself, if this relationship will work if dt is equal to 0 and dp is not equal to 0. If that's true, if that's going to work under that case, then this whole right-hand side is 0. The left-hand side is the product of two things. One of them, dp, is not 0, but the product has to be 0. Hence, everything inside the bracket has to be equal to 0. So you rearrange that to get this partial of h with respect to p holding t constants equal to, boom. That was a lot of work to get to this result, wasn't it? You substitute that into the dH relationship, and you get this is the relationship that we wanted. So what we set out to show is shown.